Because we care about our number of valence electrons for bonding behavior, it will be very useful to look at what we call Lewis dot symbols. Lewis dot symbols are really useful because all they do is show the number of valence electrons while ignoring the number of core electrons, and each valence electron is represented as a dot. So in the case of boron, for example, with its electron configuration 1s2, 2s2, 2p1, we see we have 3 valence electrons, 2 in the 2s and 1 in the 2p. And so we would represent this as taking our elemental symbol for boron B and then drawing 3 dots around it. And the location or orientation of those dots does not matter. So we can put them really anywhere. The one thing you should not do is pair them up. So you shouldn't have 2 dots on the same side, top, side, or bottom. We only pair them up after 4 electrons because we have 4 sides, 4 electrons. So here's just an example of all of our Lewis dot symbols for all of our main group elements, group 1A through 8A. So we talked about boron. If we add one more electron and proton to be a neutral atom, that's carbon. And so you see we have 4 now dots, 4 valence electrons. And if we add another one for oxygen, now we have 5 valence electrons. And as I mentioned before, it's only once we have more than 4 valence electrons that we begin to pair up our electrons. Now in the case of our alkali and alkali earth metals, the number of dots is equivalent to the number of electrons lost when it becomes a cation. And we're going to talk about covalent bonds next class, not this class, but just to give you a heads up, in our nonmetals, the number of unpaired electrons, so the ones that are just solitary on their own, is equal to the number of covalent bonds that that element can form. In addition to neutral atoms, we can also use Lewis dot symbols to represent ions. So let's take a look at sodium. In sodium, we know we'll lose 1 electron because it only has 1 valence electron in order to become Na+. And here we just represent the symbol as Na+. Notice how there are no dots around it. That's because it has emptied out its valence shell to become Na+. And it is very important that you remember to include the plus, otherwise someone reading that might just think you're referencing sodium, the neutral element. On the other hand, oxygen wants to gain 2 more electrons. So you can see it has 6 valence electrons. With 2 more, it can become isoelectronic with argon. So it will form oxygen 2-. And now when we represent this, we have to show all of the valence electrons. So here you see we have all 8 valence electrons. And now something I want to point out is that we have square brackets around my oxygen and then a 2- symbol. And the reason why we have these brackets followed by a 2- is because we know we have extra electrons in there. We have 2 more electrons than we have protons, which gives it a 2- charge. But the purpose of those brackets is to let the reader know that we can't tell which 2 electrons are the extras. All electrons on this oxygen are equivalent to each other. And so we cannot attribute the 2- charge to any 2 specific dots. So instead we just put brackets around it and say somewhere in this whole mess of oxygen and electrons there is an extra 2- charge.